Hi, so welcome back to this lecture where we will work out the solutions of the problems given in the assignment set 1. So the first problem on the set was to show that something was a group. So this is the set which is called G, which is the set of all complex numbers which follow this equation. In other words, complex numbers which are the nth roots of unity. Okay, and of course the binary operation that we're using on this set is just complex multiplication. It's plain and simple complex multiplication that we have known. So we just have to show that this is a group. So we basically have to go over all the 4 properties or the 4 axioms of being a group. So let's just do do them one by one. So the first property would be the closure property, and that would be if you take 2 elements from G, the product of them or the binary operation on both of them should be an element of G again. So if you take A and B as 2 elements of this group, we just have to show that the product is also an element of the group. And when I say product, as I've said before, I mean product with respect to this, which is basically complex multiplication. So it's a product we have known all our life. So A and B belonging to G would mean that A to the n is 1 and B to the n is 1. Okay, that's because they belong to G. And belonging to G would mean that they satisfy this equation. Can I show? So I just have to show that A dot B n should also be 1. And then A dot B would be an element of G. Okay. First of all, complex multiplication of 2 complex. So they belonging to A and B belonging to G would mean they're complex numbers. So complex multiplication of 2 complex numbers is a complex number. So this A dot B is an element of C already. So we just have to show that this is equal to 1, which would mean that A dot B would belong to G completely. Okay. Now, you know how complex multiplication works. These are complex numbers multiplied together to the power n. So you can take out this is, again, the mathematics we have done, the kind of arithmetic we have done all our life. So we're not, defining something, some special kind of binary operation here. This is an operation, this is a binary operation we have used all our life, and this is how it works, okay, for complex numbers. And because each of them is 1, this is 1, multiplied with 1. 1 again here means the complex number 1 here, okay? So 1 plus 0i, okay? And the multiplication of that would be 1 again. So therefore, this is an element of G, so it's closed, okay? So this just shows that, A dot B is an element of G, and therefore the closure property holds, okay? Number 2, complex multiplication is associative, okay? There is nothing to prove here, okay? You can take 3 complex numbers, multiply them in any order with complex multiplication, and the results will be the same. So complex multiplication is associative, and there's nothing to prove in that, okay? Number 3, the identity element. Well, 1 is an element. 1, the complex number 1, it's a complex number, and also 1 to the n is 1, so 1 is an element of G, okay, 1 is an element of G, and 1 acts like identity, because if you take any element from here, and you multiply by 1 from both sides, okay, it gives you that element back, and we know, how complex multiplication, this is the identity for complex numbers. 1 is the identity for complex numbers, and that's what is happening, okay? And then number 4 is the inverse. Well, if I have an element from G, it means it's a complex number following this equation. Then what's the inverse of a complex number? Of course, this cannot be 0. Because if it's 0, 0 to the power n would be 0, so it cannot be 1. So obviously, when I say A is an element of G, it just means that A cannot be 0. So if A is not 0, the complex number 1 by A is a valid number. Okay, it's just that, if you have x plus iy as a complex number A, if this is the complex number, then the inverse of that complex number in the complex group, if you call it, okay, is going to be x plus iy. That's it. And in fact, you can express it in the form of so this is just going to be x by x square plus y square minus y by x square plus y square. This is obviously 1 by A is an expression, but it really is a complex number. This is the real part, this is the imaginary part. So if A is not 0, then you have the complex inverse. Okay? And so what happens to this? If you take this to the power n, obviously we know how it works, how complex multiplication works, or power of a complex number works when there's an inverse like this 1 over. It's just going to be 1 over a to the n, and since a to the n is 1, we have 1 over 1, which is 1, and so therefore 1 over a is the inverse. Okay, so the inverse of a is just 1 over a. 1 over a means this complex number, where a is that complex number. Okay, so anyway, so this is a very simple example. It's the nth roots of unity. They form a group under complex multiplication. Okay, that's the first sum. Let's do the next one. Incidentally, this is also a commutative group because complex multiplication is commutative. But anyway, you don't have to check that. Let's do number 2, which says, this was one of the problems that came up while we were, doing the topic, and we said that we would give it in the assignment, and that's what it is. So this is a subgroup. So if this is a subgroup of a group, as I said, I will write subgroups in shorthand like this. Okay. This is a subgroup if and only if, in other words, you have to show both sides. Okay. Assuming this, you have to show this side and the other way around. If and only if for all x, y in S, x, y inverse belongs to S. Oh, there's a dot here. Okay, sometimes I may omit the dot, excuse me, just by habit. Excuse me, but it means that it's always there. Okay, sometimes we tend to just omit it because we understand it is always there. So this is what you have to show. Let's do the necessary side first, the necessary and the sufficient condition. So in other words, the forward side. I will assume this statement, I will show this statement is true. That is always true because it is a subgroup. Okay. Excuse me. If it's a subgroup, obviously, if two elements are there, if x and y are two elements of S, okay, y is an element of S would mean that y inverse would exist, okay, because this is a subgroup. So subgroup would mean it follows all the properties, all the axioms of a group, okay. So if I take two elements x and y from S, if y is an element of S, y inverse has to exist because the inverses exist in subgroups because they are groups by themselves. And if x and y are, so if x obviously is an element of S and y inverse is now an element of S, then by the closure property of S, x dot y inverse should also be an element of S. This is really obvious. This proof, the necessary condition is absolutely obvious. Okay, if this is a subgroup, this will have to be true. This statement, if you take any two elements, this combination will have to be an element of S. Okay, let's do the other one, the sufficient condition. So I will assume this is true, and I have to show that this is a subgroup of this. Okay. Okay, so to show that it's a subgroup of this, we have to show that all the four properties or all the four axioms would hold. So let's go over them one by one. The closure property, or let's do whichever one comes first. Okay. So one thing that is obvious is if I take, so let's assume something. We take that S is not, when I take this, when I assume this statement, I'm assuming S to be a subset of G, which I will then show that it is a subgroup. Okay, not any subset will be a subgroup. It has to follow the four axioms. So when I say, when I'm assuming this statement, I now assume that S is a subset of G. But let's assume that it is a non-empty subset. Okay, it's a non-empty subset of G. So when I say it's a non-empty subset, I can take any element from S. Okay? If I take an element of S, which I call Y, I mean, you can think of having two elements. Instead of taking X and Y, you think of taking, because Y is an element of S, think of taking it twice. Then, because this statement is true, I know that Y dot Y inverse is an element of S, but Y dot Y inverse is 1, which is the identity in G. So the identity element belongs to S. So that proves the identity part. The identity element in G actually belongs to S, because this is true and S is non-empty. Okay? Well, let's take another one. What happens when the identity is there? Well, if the identity is there and I take any other element, so I want to prove the inverse now. The identity is there. In the second point, I want to prove that the inverse statement is true. In other words, if you take an element Y from S, you can show that Y inverse also belongs to S. So let's take an element from S. We now know that the identity belongs to S. Okay. So let's use this. Let's think of 1 as X and Y as this Y. So that would mean that X dot Y inverse is an element of S, but 1 is the identity acting on an inverse, well, any element, it keeps it what it is. So taking Y as an element of S tells you that Y inverse also belongs to S. So that's the inverse property. This is true for any Y. I've just taken a very general Y, not a very particular Y. So identity is there, inverse is there. What about closure? Can we do closure? Well, if I take X, so to do closure, I have to take two elements, X and Y, from S. I have to show that X dot Y belongs to S. Well, we just showed before this that the inverse exists. So if Y is an element of S, this would mean that Y inverse belongs to S. Okay. So now I have X belonging to S and Y inverse belonging to S. So think of it like this. X is an element of S, and instead of Y, think of Y inverse as an element of S. So if you combine the two, this would mean that X dot Y inverse is an element of S. Correct? Because if you take two elements, the second one inverted multiplied by the first belongs to S. So if I take these two now as an element of S, so X, Y inverse, the second one gets inverted again. But we know that we've done this while we were doing, powers and orders of elements. All rules for multiplication or all rules for indices remain the same. So inverse is -1 multiplied by -1, so that is 1. So this is really XY. Okay, if you want, you can go back to that lecture where we said that we have actually proven that all rules for indices of an element remain the same. So -1 to the -1 is just 1. Okay, so here is the closure property. Therefore, two elements, their combination or their multiplication is an element of S. What about the associative property? Well, the associative is true because we are using the we're using the same binary operation for S. Because this operation was the operation used in G, which was a group, and so by default, this would be associative in this. And so therefore, because we're using the same binary operation here, or restricting that binary operation to this subset, this must be associative here as well, okay? So this is associative, okay, by restriction, okay? Just by restriction, because we are restricting the same operation on G to S, okay? And in G it was associative. So therefore, that's the second solution of the second problem, and so both the sides hold. So yeah, that's the if and only if condition. Let's do the third one. Problem 3 says that G is a group, obviously, and A is an element of G. You know, G with the dot. And the order of this element is n. Suppose K and n, K is another positive number, okay, another positive integer, such that K and n are relatively prime. So that's written like this, as a HCF, the highest common factor. The highest common factor is 1, means they don't have any factor dividing both the numbers except 1. Okay, so that's another way of saying relatively prime. So no common factors except 1. Okay, we have to show that the order of A to the K, which is another element of G, it's just A multiplied K times, okay, this is also n. That's what you have to show. Okay, let's do this. So first of all, we have to show that this order comes out to be n. But for now, let's assume that let the order of this element, A to the K, be some element, some number, some positive integer m, okay? We have to show that m will turn out to be n, okay? But let's start with some positive integer n, okay? It has to be a positive integer. It's an integer but positive, okay? Because that's what orders are. They're positive integers. First of all, okay, what's given? Order of A is n, that is given. So A to the n is 1, that much we know. And n is the smallest such element, smallest such positive number such that A to the n is 1, okay? That much we know. We have taken, okay, so if the order of A to the K is m, then this is also 1. This is the element raised to the order m is 1. Okay, but that's the same as saying A, K, N. You can Km, you can multiply the indices because all the rules of indices multiplications would hold. And so this is 1. So if you take order of AK to be m, then A to the Km must be 1. But if the order of A is n, then and A to the Km is 1, then n will have to divide Km. You know, this is one of the results we have shown, that if you order of something, order of an element is n, and if you have a to the some other number, other integer which is 1, then the order which is n must divide that integer. Okay, this was one of the results, one of the big results that we have shown, or important results that we have shown in the lectures before. So if the order of a is n and you have a to the km as 1, then n must divide km. But k and n are relatively prime. In other words, n cannot divide m. There are no common factors between n and m except for 1, which is common everywhere. So the only way that n can divide k and m is if n divides m. Okay, you can think of an example. I mean, what if I say that 5 divides 2 and something here? Okay, can I say 7? No, because that's 14 and 5 cannot divide 14. I can put a 10 here. Okay, I can put a 10 here, or let's think of it like this. What if I say 5 divides 20? Okay, but 20 can be written as 2 into 10. Okay, but 5 cannot divide 2. Or they have no common factors except 1, so 5 will have to divide 10. Okay, like that. Okay, if 5 cannot divide 2, the only possible factor here must be a multiple of 5. So therefore 10, 15, like that, something like that is valid. So if n and k don't have any common factors except for 1, then the only possible choice for m must be that m is a multiple of n. Okay, so right, so we have a result here that if you take a to the k, if you take the order to be m, then necessarily n must divide m. So to be an order of ak, what should it satisfy? Let's look at it. First of all, this must be true. Ak to the m must be 1. And number 2, now we show that n must divide m. So to be an element, to be an order of a to the k, m must satisfy these two conditions. A to the k to the m must be 1 and n must be dividing m. But we need m to be a number which is the smallest, which would satisfy these two conditions. And then, because order means the smallest number would satisfy this condition, order of this element is the smallest number which would satisfy this equation. Okay, we need m to be the smallest number. Well, we already have a number in our hand, which is n. Let's see if n satisfies these two conditions. A to the k n, I'm seeing if n satisfies these two conditions. In that case, n would be a candidate for the order of a to the k. That's what we want. Well, a to the k to the n is the same as writing a to the n to the k, because we know that all properties of indices hold here. So now a to the n is 1. We that's already given. So it's 1 to the k is just 1. So yeah, that is true. So n does satisfy the first property that an order of a to the k must satisfy. What about the second property? Does n divide n? Yes, of course, n divides n. So n is one candidate which satisfies both the properties of that it should to become an order of the element a to the k. But the question is, then, which is smaller? Does m be smaller, the smaller number, or n the smaller number? Well, what's the smallest number that n can divide? N. Okay, the smallest number that n can divide is n itself. And if n satisfies the first condition too, then n has to be the smallest number which satisfies both the two conditions to be the order of a to the k. And therefore, this would imply that the order of a to the k must be n. Because we needed the smallest such number m. It's the smallest number possible. And turns out that n is the smallest number which satisfies the properties that it should to be an element, to be the order of a to the k. And therefore, order of a to the k is n. Okay, so that's one argument for this proof. Okay, all right. That proves it. So it's a very important result in the sense that if you have an element whose order is something that is given already, and of course we're dealing with finite numbers here. Okay, n. When I say n, I mean n is a finite number. I'm not saying n to be an infinite number. In fact, that is true as well. If n is an infinite number, it would be true to say that the order of a to the k would also be infinite. Okay, just a side note here: if the order of a is infinite, in other words, if n is infinity, what that means is a to the 0, a to the 1, a2, all of them, this sequence here will never end. Okay, that's what it means that order of a is infinity. This sequence never ends. Okay, then what about this sequence? Ak to the 0, ak to the 1, ak to the 2. What about this sequence? Will it end? Well, this will also never end because this will be a subsequence of this. For example, let's take k to be 3, just for fun. Then a3 to the 0 is just a0. Okay. a3 to the 1 is a3. a3 to the 2 is a6. So basically, when k is 3, the sequence 8 to the 3, 0, 1, 2, like that, this is this sequence. Well, it turns out a3 is here, a6 is there, a9 will be somewhere there. So if this sequence a0, a1, a2, if this is a non-ending, never-ending sequence, then this subsequence a to the 3, a to the 6, a to the 9, this is also a never-ending sequence. So this is also, so a to the k 0, 1, 2, this is also a never-ending sequence, and so that just means that the order is again infinity. The order of an element is infinity means that this sequence goes on and on. This is never ending. So this is true. This result is true for any n, whether this is finite or not or infinite. Okay. If n is infinity, it is infinity here as well. All right. Let's do number 4. Which was the proof of Lagrange's theorem, and there are a few parts to it. So, number 4, and in this one we are proving Lagrange's theorem, which is a very important theorem. Lagrange's theorem, which really says that if G is a group and the order of G is finite, okay, it's a finite number. In other words, it has a finite number of elements in G. And if S is a subgroup of G, then the order of S will divide the order of G. In other words, the number of elements in S will always divide the number of elements in G, which is a very, very powerful result. For any finite group, in other words, with finite number of elements, if you take any subgroup, the number of elements in S will always divide the number of elements in G. It's very simple and a very powerful result. And we do this by doing a few parts to it. The first part is to show, in the first part, we've defined what is a coset. So if you take G to be any element of capital G, small g is an element of capital G, then the left coset is defined as, or it's written as, it's denoted as GH, S. We're using S here as a subgroup. You can put that dot here, or you can omit it, but remember, this dot should remain. I mean, it's part of the notation. This is defined like this. So it's the multiplication of all elements of S by this element G from the left. That's why we call it the left coset. Okay. We don't know whether the multiplication will be the same if you multiply G from the right, because we're not asking G to be a commutative group. In other words, we can exchange the positions of multiplication of the elements that we are multiplying. If it's a commutative group, it doesn't matter in which order, or whether you swap the positions of the two elements. It doesn't matter. But as long as G is a general group without any extra structure of commutativity or abelian added to it, we call the left multiplication by this small g as the left coset. Okay, so this is small s. Let me just write. Okay, where small s is an element of the subgroup. Okay, so all elements all elements of S multiplied by G from the left. As an example, if you think of the group Z star, that is Z, the integers without, let's not do integers. Let's do Q star. I mean, let's say I take the element Q, which is Q star, and multiplication. Okay. Then if I look at let's write multiplication as dot. Okay. Normal multiplication. If 2 dot Q, what kind of elements would if I take a subgroup, this is a subgroup of, let's say, R star with multiplication. Okay, and if you think of 2 dot Q star, what kind of elements would you have here? All rational numbers multiplied by 2. Okay. Well, it'll turn out to be Q star itself because 2 is a rational number. But, it really means if you take a number PQ from Q star, you just multiply it by 2. All such numbers, okay? So, in other words, if the number you take is 3 by 4, that number becomes 3 by 2. Okay, so all numbers that you can pick from Q star are just multiplied by 2 from the left. Okay, so that's what it means. Okay, so something like that. All right, so that's a left coset. The question is, show that two left cosets will be the same if I take two elements from G. Show that two left cosets will be the same if and only if, in other words, both sides, A inverse B is an element of S. Okay, so this is what we have to show. So we've defined what is a left coset. So AS means multiplication of all elements of S by A from the left. Again, I'm missing the dot here, but really the dot is always there, okay? So first let me assume that this statement is true. So, and I will prove this one, okay? So if this is true, in other words, remember what this is. This is a set. This is a subset of G, okay? Because if you multiply S by small g from the left, in other words, if you multiply all elements of capital S by G from the left, these are all elements of G because dot is closed. Okay, remember S and G, they're both elements of capital G. Okay, S is only a subset. It's a subgroup, but it's a subset. So these are all elements of capital G. So the whole set here, the left coset, has to be a subset of G. So the first thing that I'm assuming is that these two subsets, they're not subgroups. I've not said that this left coset will be a subgroup. Okay. In fact, they will not be a subgroup. Okay. So when I'm assuming that these two sets are equal as sets. Okay. In other words, they have the same elements. Okay, they have the same element, exact same elements. If 5 is here, 5 is there too. If 7 is here, 7 is here too. And you just have to show that in that case, A inverse B must be an element of S. Alright, let's just do that. So, first of all, if I want to show this is true, let me assume that, let me take the letter B. Okay. Now, it's important to understand, or before I do this, let's analyze this BS, this coset, left coset. I'm claiming that B is an element, this small b actually belongs to the coset BS. Why? Because S is a subset of G, and so 1 is an element of S, and I'm multiplying all elements of S by B on the left. Okay? So when I multiply B to 1 on the left, this must be an element of BS. Because BS contains multiplication of all elements of S by B on the left. Okay. So, and this is B. B multiplied by 1 like this is B. Does that make sense? So, BS necessarily would contain the element B because 1 is an element in S. The identity is there in S. So, just multiplying that by B gives you B. So, B has to be an element. So we need that little fact there, okay? So I'll just write it down. That's a very one-line proof. It's very easy. So B is an element of BS. That has to be true because 1, the identity is here. If B is an element of BS, assuming that BS is equal to AS, if BS is equal to AS, the two sets, so B must be an element of AS because the two sets are the same. If B is an element of AS, then B can be written as A times some element of S. Because what does it mean to say B is an element of AS? AS contains these kind of elements. So B has to be one of them. And okay, is that clear? So if B is an element of this kind, A times an element of capital S, the subgroup, then I can multiply by A inverse on both sides. I will have A inverse B, and A inverse on A will give you 1, the identity, again, I'm using associativity now. I don't care in which order I'm multiplying. I'm first multiplying A inverse with A from the left. That gives me 1, and 1 with S gives me S. Okay? And that's an element of capital S, of course. Small s is an element of capital S. So that's what we have shown. A inverse B is an element of capital S. Just because B was an element of BS, and so it had a form like this because BS was equal to AS. And so then just by a little multiplication by A inverse, this is true. Okay, what about this side? If I assume that this is true, I have to show that these two sets are equal. Now, what does it mean to say that two sets are equal? So when I suppose I have two sets, X and Y, how can I say that they're equal? The way I can say that two sets are equal is if I can show that if I take an element small x from capital X, any small x, and if I can show that small x also belongs to Y, then I have shown that X is a subset of Y. In other words, I have not taken any particular element, I've taken a general element of X, and I've shown that any general element of X is also an element of Y, so X will have to be a subset of Y, because all elements of capital X will be elements of Y. Similarly, if you take an element small y of capital Y and you show that that small y also belongs to capital X, it means that any element of Y is an element of X also, so that means Y is a subset of X, and if one is a subset of other and the other way around as well, these two would mean that X is equal to Y. So that's the trick that we will use. That's the trick that we will use to show that these two sets are equal. First, I will take an element from, let me think of this as X and think of BS as Y. I will take an element from here and I will show that it belongs to BS. That way I show that this is a subset of BS, AS is a subset of BS, and the other way as well. So let's just do that. So let's take an element X from AS. Okay? But of course, we know what X would look like because it's an element of AS. It would look like A multiplied by some element, small s. Okay, I have to show, I can call this X. I have to show that X belongs to capital Y or small bs. Okay. Now I'm assuming this is true. So what is this? What does it mean? It means that if this is an element of S, so A inverse B must be some element of S, which let me call S0. S naught there, okay? I'm just assuming that A inverse B is an element of S, so let me just give it a name, S naught. Okay? So, right, I have to show that X is an element of Y. But X is AS, and what can I write? How can I write? What can I do with this here? Can I express A in terms of B? Well, this actually translates into A equals B S0 inverse. I hope that's true. I mean, you understand that is true. Because, we've said this, we can use any multiplication, kind of multiplications that we have done all our lives. So you can multiply by A on both sides from the left. This would be reduced to B because A on A inverse gives you 1 and 1 on B gives you B. And so you have, so basically what I've done is this. I've multiplied both sides by A on the left. So the left hand side gets reduced to B and I have A S0, and then I multiply both sides by S0 inverse on the right. So I have B S0 inverse here, and S0 inverse on S gives you 1, and so really A is B S0 inverse. So A here I can write as B S naught inverse, which is A, and then the S. Okay, so X really takes this form, but of course by associativity I can just look at this like this. and then think of multiplying by b. But this is an element of capital S, because these are all elements of capital S, and capital S is a subgroup. So it, by closure property, this is an element of capital S. So small x takes up a form where it is the multiplication of b on the left of an element of capital S, so x has to belong to Bs, because this is an element of capital S. Okay, so x, I took an element of small as, and I've then shown that it's an element of small bs, so therefore as is a subset of bs. That's the first part. What if I take y to be an element of bs, the other way around? I'm now taking y to be an element of this set, but of course y would take this kind of a shape. Let me call it S1. It can be a different element. Okay. Now, so I have to show that y is an element of capital X. So I have to somehow write a times something here to show that small x is y is an element of capital X. So let's just do that. What can I do? I have to change b to a somehow, but I have this equation. Well, this is, as I said, this is also the same as b is a is 0. Okay, just multiply both sides on the left by a. So you have b here and you have a is 0 there. So b can be written in terms of a like this. So let's change the b here and write it a is 0. And then of course there is an S1. So let me just put that here. And so now it takes the form of small as, because then of course it's in this form. Small a multiplying some element of capital S. And so therefore y, which is an element of small bs, is an element of small as. So bs is therefore a subset of as. And so this is true. As is equal to bs. Okay? Alright, so that's one part of this proof. Okay? So it's important. It's a result which actually tells you when can two left cosets be equal. It will be equal only when A inverse B is an element of the subset S, or the subgroup S. Okay? So that's a result that we can use freely from here on in. Okay, it's an important result to remember. Okay, let's do number 2 or part 2. What's part 2? Okay, so we have to show from the first part, we have to conclude that either two left cosets are equal, in other words, as subsets they are equal, or they are absolutely disjoint. That's a very strong result. In other words, two subsets will be either disjoint or they will be exactly equal. So that, as concepts, they are absolutely opposite of each other. Okay? Two subsets can be either equal or absolutely disjoint. That's a very strong property that left cosets follow. Let's just see this. So either this or this. How do we show this? So if this is true, if I assume this is true, then we are done. Either means either I have to show this is true, or this is true, or you can show that both are true. Okay, but showing that any one of them holding is enough to prove this. So the way I can show this is, if I assume AS is equal to BS, we are done. So let's assume that AS is not equal to BS. Okay? In that case, we have to show that they will be disjoint. It would be better to show the other way. If I assume this is true, then we are done. If I assume this is true, then we are done. But let's say that this is not true. In other words, this is non-empty. Then we have to show that this is true. Let's see if I can show this is true when this is non-empty. This intersection is non-empty. This intersection is non-empty means there will be an element in this intersection which will belong to both the left cosets, AS and BS. But it means that it takes both shapes. It takes A multiplying some element of capital S, and it also is B multiplying some element of capital S. Okay, X belongs to both the sets, so it has to look like elements of both the sets. Of course, we don't know which these two S's can be different. Okay, the S1 and the S2. All right, we have to show that this is true. Okay, again, you have to show that two sets are equal. We will use the same technique. I first assume an element from here and I show that it belongs to there. Let me take an element from here, which I will call small as an element of A capital. I have to show that this is an element of BS. Okay, how can I write small as? I should change into this to B into something. B into some element of capital S. Okay, same technique. Can I use this here? This equation. Can I write A in terms of B? So from here, I think what's true is A is equal to B S2 S1 inverse. I hope everyone can see that. Okay, just multiplying by S1 inverse on both sides on the right. So A can be written as B S2 S1 inverse, and then of course you have that S here, and because of associativity I can think of all these elements multiplying first and then B, and that's an element of BS, because all these are elements of BS, and by closure these are all elements of S, and by closure these are all elements of capital S. So therefore this AS takes the shape of being an element in BS. And so AS is a subset of BS. Similarly, if I take BS to be some element of this left coset, B capital S, then I have to do exactly the same thing. I just have to write BS in terms of A something, and I can do that again. I know what it is. From here, I can say that I have to change B to A. So B can be written as S1 S2 inverse. Multiply both sides by S2 inverse on the right, and you will get it. A. Multiply both sides by S2 inverse on the right. And so, therefore, B is this, A, S1, S2 inverse, and then I have this S. Again, by associativity, I don't care about, or I can put my brackets on this one first, and that looks like an element of AS, and so therefore this is an element of BS is an element of AS, and so BS is a subset of AS, and so this is true. So that proves the second part. Okay, if you assume this is true, then we are done. If you don't assume this is true, you have to show that this is true, which we have shown. Okay, so that's a very, very strong property that left cosets follow. Okay, in fact all cosets, but we are doing left cosets now. Right, what's the third part? The third part says show that the number of elements in a left coset is the same as the number of elements in the subgroup S. Remember, this is a subset. AS is a subset, not a subgroup. And this is a subgroup. Actually, this S is also a left coset. This is 1 multiplying S. And if you want, you can show this, okay? If you want, you can try and show this. It's a very easy thing to show. The subgroup can be written as a coset, left coset. Again, these are two sets which you have to show they're equal, so you can use the same technique. An element from here is an element in here. An element from here is an element in here, okay? You can do that. Okay, so we have to show this. And the hint that was given in this part was to show that all elements of this left coset are distinct. In other words, if you take two elements of this left coset, AS1 and AS2, if you take two elements from this left coset, show that they are distinct. No, show that they are not equal. Can we show that they are not equal? Okay. When can they be equal? When can they be equal? If I assume they're equal, then I can multiply both sides by A inverse on the right, and I would just have S1 equals S2. But S1 equals S2 would mean that I have chosen the two elements chosen the same element twice. Does that make sense? Okay. So if I assume that I have taken two distinct elements, if I assume that x1 which is not equal to y, and they're both elements of AS, so the first element is AS1 and the second element is AS2, and I have taken two distinct elements. Okay. Then, if I've taken two distinct elements, in other words, two different elements, then it's necessary that S1 and S2 are different. Okay? Because if S1 and S2 are same, then AS1 and AS2 are same, and so X and Y will become the same. Okay? So, therefore, all elements of this will have to be distinct here. Okay? So, for example, if S is like this, if S is S1, S2 up to Sk. Okay, we're dealing with finite groups. So S is a subgroup, so it's a finite subset as well. Okay, the question is, so what is AS? It really is like this: AS1, AS2, ASK, something like this. Okay, A multiplying all elements of S. So question is, are they distinct? Are they distinct elements? Yes, because, for example, AS1 and AS2, these two are distinct because S1 is different from S2. Is that clear? Okay. Because here in this list, when I'm listing the elements of S, I've not repeated any element. I've not repeated S1 here, S1 here. S1 and S2 are distinct elements. Okay, I've listed each element only once here. So I've not written 2, 2, 2, 3 times. I've written 2 only once if 2 is an element of S. Okay. So if S1 and S2 are different, then AS1 and AS2 will have to be different. Because if they're equal, it would mean that S1 is equal to S2, which is not what we have done. Okay. So if they are different, if all of them are different, then all of these will have to be different. Okay. So they're all distinct. So all elements of AS, this left coset, are distinct. Okay. If they're distinct, then we can just count how many elements are there. There are k of them, 1 to k. And here there are also k of them, 1 to k. So therefore, the orders will be the same. Okay, that's a very simple argument. Okay, it's just that because of the left cancellation law, you can show that if all these are distinct elements, these will have to be distinct elements. Okay, and therefore, the number of elements in a left coset will be the same as the number of elements in the subgroup S. Okay, and we'll now do the last part. Well, actually, the last important part, the final part is just to show that, just to conclude this property. So the fourth part is this. It shows that, so G of course is finite, the order of G is finite. So show that G is equal to the union of some subsets . Some left cosets. You have to show that G can be expressed as a union of some cosets, some left cosets like this. Okay. Well, let's see. Let's do it. Let's look at it by an example. Suppose because G is a finite group, in other words, number of elements is finite. Let's say that there are 7 elements, G1, G2, up to G7. Then, if I take G1S, G2S, if I take all the left cosets, S is some subgroup of G. In other words, it's a some part of G. Okay. If I take all the left cosets of S, if I take the left cosets of S by all the elements of G, from G1 through GS, the question is, G can be written, I'm asking this, can G be written as G1S union, G2S union? Can this be written as this? Well, first of all, these are subsets. G1S, G2S, these are subsets of G. So the union is a subset of G. So this side is true. This set will be a subset of G. Is this a subset of this side? Then the two will be equal. Well, if I take an element from here, let's take G5. G5 is an element from G, but then G5 actually belongs to G5S, right? And G5S is somewhere in here. We've shown that. G5, this element which is forming the left coset, will necessarily be an element of the left coset. So if I take an element, any element from here, it will be an element of one of the left cosets. So it will be an element of the whole union. If it's an element of one of the cosets, it's an element of the entire union of all the other cosets. So therefore, this side is also true. Okay, an element from here is an element from this union. So the two are equal. Okay. So it really can be expressed in terms of as a union of, different left cosets. The only question is, are all these left cosets distinct? In other words, we have seen that either two left cosets can be exactly same, in other words, as subsets they are the same, or they are absolutely disjoint. Okay, so maybe let's say that if, for example, there are seven left cosets. Let's say G1S and G2S are the same, and that we have seen that it's possible. Okay, and say G3 and G6 and G7 are the same. Okay, either they are the same or absolutely not same. In other words, absolutely disjoint. Okay. In that case, if let's say this is what it is, then G can be written as, capital G can be written as G1S. Well, I don't have to take the union with G2S again because G1S and G2S are the same. I take the union of the same set, it is the same set. I go on to G3S. G3S, G4S, G5S. Can I take the union of G6S and G7S? No, I've already taken the union. They're the same. So it means taking the union with G6S is the same as taking the union with G3S, which I've already taken here. So there is no need to take union of these two elements, these two sets here anymore. So I can really, so even though you can take the union of all the left cosets, but it's absolutely fine if you take the union of only those distinct cosets, because the rest of them will be included, because some of them are equal. And so you can just give it a name. So this is like A1, A2S, A3S, A4S. So really, G here, which had 7 elements in them, is actually a union of 4 of its left cosets, because some of the left cosets are the same. So therefore, G, and we have shown that the two sides will be the same, but G can be expressed as a union of a few of its left cosets. And that's the proof. I've left this place blank. I've shown it by an example. And you can generalize this by the letter M here and say N here as I have written it. Instead of 7, I can write M. Instead of 4, I can write N, and that's the proof. Okay. So really, G can be expressed as the union of all these subsets, which are left cosets. That's the proof. So the final part of this was to show that this, therefore, the order of S therefore divides the order of G. How do we show this? Well, if this is equal to this, let's say the order of G is M, as I was suggesting here. There are M elements in G, and the order of elements in S is K. Okay, there are K elements in S. Okay. Now, if I go back to my argument from here, which are the left cosets I had included? The left cosets that I had included here are the ones which are absolutely disjoint. Because while taking the union, I have discarded the left cosets which were equal to one of them. But the ones which are not equal, for example, A1S is not equal to A2S, then these two are disjoint sets. So you can think of G as this whole set, and A1S is this one, A2S is absolutely disjoint from A1S, A3S is somewhere here. Okay, so you can think of all of these left cosets as disjoint. So this is A1S, this is A2S, and you know, this whole thing is G, and you can fill up all the way up to ANS. Okay? Because I've not included the ones which are already equal to all of them. Okay? Or any of them. So therefore, the number of elements, this is called a partition. It's a set, the entire set G is partitioned into smaller sets. Okay? So therefore, the number of elements in G must be equal to how many partitions are there? There are n partitions, because there are an element, ans, you know, the order is up to n such partitions, and each partition has, for example, let's just write it like this. This order will be the order of A1S plus order of A2S. In other words, number of elements in A1S, the number of elements in A2S. I'm just summing the number of elements. because they're all distinct, they're all disjoint, there is no overlap. So I'm not counting any element twice. So this goes on till order of ANS. And in one of the parts I've shown that the order of AS is the same as the order of S, just the previous part 3, I guess. Okay? The order of any left coset with S, left coset of S is the same as the order of S. So these are all, they all have order of S. N times. So n times, all of there are n of them, you have order of S, and so really, order of, you can divide by order of S, so order of G by order of S is equal to n, which is a positive, which is a natural number, it's a positive integer, and so therefore this order of G is divided by order of S, because this turns out to be a positive integer. Well, we did not need to give them names, but it's okay. So therefore, this is true that if you have a finite set, then the order of any subset of it will divide the order of G. Okay, and that's how it is done. Okay, and the important thing is that G can be expressed as you can call them disjoint union. In other words, the sets which are here are disjoint from one another. They are the disjoint union of some cosets of G. Okay. All right. I think that finishes Lagrange's theorem and the solutions to the problems given in assignment 1. We have learnt many new things. We've learnt about cosets. We've also gone over orders of elements and everything. So it's important to understand these techniques that we have learned through the solutions as well. So we will take things forward in the next lecture again. Thank you.